Welcome. I want to quickly get back to this spectral estimates, which is quite exciting. So we can estimate the case eigenvalue of the Kirchhoff Laplacian of an arbitrary graph using the degrees, the vertex degrees. I want to say a little bit more about the proof of this theorem, also a little bit maybe about the history and related mathematics. First of all, the case k equal to n, which is a spectral radius, is already interesting. The spectral radius is probably the most studied eigenvalue, except maybe lambda 2, which is the first non-zero eigenvalue in general. But the spectral radius is very important, and there is a nice estimate which is due to Anderson and Morley, which I'm going to say something about, which is a little bit of supersymmetry already. I just generalized this formula of Anderson-Morley from k equal to n to arbitrary k. So if k is 1, then this is 0. So we assume just these 0 formally to be 0, so that this formula holds for every k. It's very exciting to have a result which is true for all graphs. It's not just a special class of graphs, it's for all graphs, or a whole category of objects. And it's very general also in the sense that we can estimate all the eigenvalues. So I'm really excited about it. And so I'm so excited that I really decided to submit this. I usually do not submit papers to journals. I don't need papers, but so to have I think this is something which is really cool. There's also a lower bound which is unrelated, but you can also estimate the lower below, the eigenvalues below, in general, using the vertex degree. And there's this formula here which Jiming Guo has conjectured in 2007, and then Brouwer and Hemmers have proved this. And I think 1 year later, and it was special cases also have been known before, like Lipan has taken the case of n-1, the second largest eigenvalue. So Cauchy's interlacing theorem deals with a principal matrix, major principal matrices, where you just delete the case row, case column. So you're interested with what happens with the eigenvalues if you do that, or more generally if you delete even more rows and columns. So if you have two polynomials, one has polynomial has degree n, that would be the characteristic polynomial of the whole matrix, and then the polynomial g, which is the characteristic polynomial of a major principal submatrix. So this is an n has degree n-1, and you can ask yourself what happens with the roots of this polynomial. The roots of the polynomial, of course, are the eigenvalue. So there's a general interest which comes from much older times, is about what happens with the roots of polynomials. So there's a theorem of Hermite and Biela. This is quite interesting historically. I have to look at this a little bit more. So if you have two polynomials which interlace, first of all, interlacing means that the roots are just alternating. You can write them down in alternating form. And here, actually, this should be said strictly if these are real inequalities, strict inequalities. And then this means that the f plus ij has the roots only in the upper half plane or lower half plane. It's not a difficult proof, so you have to work a little bit using the intermediate value theorem and all kind of beautiful mathematics in the complex plane. And from this one can then get the result that f and g interlace if and only if linear combinations. You can actually take here linear combinations af plus bg, but this is the way which is better for the Cauchy interlace theorem if these have real roots for all a. And so also here one of the authors is the if and the other one only. Also here this is attributed to a Japanese mathematician Kakeya, who is for the Kakeya problem, variational problem, and results from theory of polynomials, which is also relevant in the theory of orthogonal polynomials. You have orthogonal polynomials and they interlace, interesting from many different points of view. And then there is a beautiful derivation of the Cauchy interlace theorem, relating it to this Hermite-Kakeya theorem. And so what Fisk did, Fisk is one of my heroes, who also appeared in graph coloring. These Fisk manifolds I talked about. What happens is he just wrote down a symmetric matrix. This is a symmetric matrix here, partition symmetric matrix. And by the linearity of determinants, you have this identity here. So it's the determinant of this matrix plus the determinant of this matrix, because we don't change anything here. We add the part up. This is linearity of the determinant. This is a real matrix. Has real eigenvalues because it's a symmetric matrix by the spectral theorem. So this is real, only real. real eigenvalues, real roots, and so here the characteristic polynomial has only real roots. In this case, we have if you look, this is actually the matrix, the Kirchhoff matrix, or the matrix under consideration in the Cauchy interlace theorem. So this is the matrix K, the larger matrix K, which has here been written as a partition matrix. If you look at this characteristic polynomial, it's just A times G. A times G. G is the characteristic polynomial of M. And here this is a characteristic polynomial of K is F. And here this is something which is only real roots. So it's directly from this Hermite-Kakeya that you get the Cauchy principle, Cauchy interlace theorem. And that's really a crucial theorem for the result. Actually, about the proof is by induction. But what you can do is when you look at the proof and you take away one of the rows and one of the columns, so you have a major principal submatrix. What happens is that you have this interlacing situation, like in the Cauchy. And I want to say something more about this Anderson-Morley bound, which is somehow a supersymmetry argument. So what you have in general, which is kind of for if you look at matrices F and G, then you can look at FTG. So these are n times m matrices, and FTG is a square matrix. So FTG is a m times m matrix, and FGT is a n times n matrices. So they are different. But so if you look at GFT, that would be the transpose of that. Of course, they have the same eigenvalues, but this is not so trivial that all the non-zero eigenvalues are the same for these matrices. There's a nice article of Dive who kind of showed in a couple of decades ago how this has applications, many applications in spectral theory, in partial differential equations, etc. So this is a very, very important thing, that the AAT and ATA non-zero eigenvalues are the same, which is really cool. One of the ways one can see it, you can look at this, essentially the characteristic polynomial. If you would scale this, if you divide by x and call this lambda, then you would have the characteristic polynomial of FTG. So you can just see that the characteristic polynomial of FTG is the same as the characteristic polynomial of FGT. And this formula, which is I call this a generalized Cauchy-Binet formula, but it's new. I've never seen that before my paper, which is very cool. It's especially interesting in the case x equals to 1, where you have a Fredholm matrix here, 1 plus the matrix, and so you have the you can write down. So essentially, you can write down the coefficients of the characteristic polynomial of a product of two matrices, which is really cool. So especially in the case when f is equal to g, that also is, then you have a square here. This is Pythagorean result. But this obviously is independent of whether you take f, what order you take for f and g. So this is or whether you take f, replace f with ft, or g with gt. This is summing over all patterns. So this also includes the empty pattern where you have an empty submatrix, where it is just 1. One of the consequences is, if you look at the diff grad, right, that's the Kirchhoff matrix, is the divergence of the gradient, right? The divergence is d star, and d is so this is the zeroth Laplacian, like the zeroth Laplacian in calculus, diff grad, and that's then the dd star is the one form Laplacian, if you don't assume any, higher orders, if you don't assume any triangles, If you don't count the triangles, I always count the triangles and tetrahedron and whatever also as part of the thing. And so graphing graph theory, you can also look at, in general, at the higher order K-form Laplacians. So all the cohomology, when you compute the cohomology, then you're using these matrices LK. So the kth Betty number, for example, is just the nullity of the case LK. So this is the non-zero spectrum of the even forms, and the odd forms, this is the same. Can also be seen using the Dirac operator, d plus d star, the formula for the Euler characteristic of the graph. The Euler characteristic is the number of vertices minus the number of edges plus the number of triangles minus the number of tetrahedra. So in this case I have 2 tetrahedra minus the number of hypertetrahedra, etc., etc., etc. So this is the Euler characteristic. This is a super trace of 1. So that's pretty cool. So that's a little bit of context of this Anderson-Morley bound. And also one should then see that when you look at the one-form Laplacian, what it actually means. So the one-form Laplacian deals with functions on edges. These are the one-forms. One-forms are functions on edges. And so what you have is, if you look at the entry of this, call it K1 here, K1ij is just the, so it's just the number of other edges with which it intersects. Of course, if you take an edge and you look, so it's the degree of on both sides which matters. So this intersects with 1, 2, 3, 4 neighbors. So this is maximally dk or dn plus dn minus 1, where dn is the largest vertex degree and dn minus 1 the second largest vertex degree. And then in the diagonal you have 2's, because it itself intersects somehow by itself. You count this as 2. But that's just the linear algebra of this K1. But then if you look at that, that's just, in general, you have for the spectral radius, you can just look at the sum of the absolute values of the kth column and the maximum overall k. That gives you an upper bound for the spectral radius. And so in this case, it's just dk plus dk minus 1. That's the whole argument. That's the proof of Anderson and Morley. But it's that essential idea that K0 and K1 are essentially isospectral. The non-zero eigenvalues are the same. And then there's a whole industry for that. You can of course do that then for if you want to estimate, for example, the spectral radius by taking K1 square. So if you take, then you get more, more neighbors are involved, and you get better estimates, but usually much more complicated formulas. To prove the thing, you can prove much more general result. What you can take is you can actually take a Kirchhoff matrix and you take a reordering of the decays. Right? The decays are then just, in general, normal vertex degrees, no more an interpretation as vertex degrees, but have an interpretation as just diagonal entries of a matrix. By the way, if you are looking at this, what you do is, in order to kind of discover this, or also to test this, you take a random graph, you build a random graph, you order it, so that's kind of a nice, interesting exercise in programming, to order this so that the vertex degrees are, the basis is chosen so the vertex degrees increase. And then so you have actually kind of the decays are just the diagonal entries, non-decreasing. And then you look, and then you delete a couple of rows and corresponding columns, and you look at the eigenvalues, and you look at the dk plus dk minus 1, and you see whether this is ever different. And you run it for tens of thousands or hundreds of thousands or millions of different graphs, and you look whether you find a counterexample. And if you don't find one, then you can get confidence to prove a more general result. So that's what I wanted to say here.